Well, class, welcome to episode 18 of our Math 1050 class on college algebra. I'm Dennis Allison, and I teach mathematics here at UVSC. In the last episode, we introduced logarithms near the very end of that episode. And if you remember, sort of the fundamental idea of a logarithm is an exponent. Let me just work a couple problems real quickly here at the beginning to sort of tie today's episode in with the last episode. If we go to the green screen, you remember that if we have an expression something like 4 to the second power is 16, we say this is written in exponential form. But there is another way of expressing this called logarithmic form. And what we do is to take the base over here, base 4, and write that as a subscript. And the number 16 we put inside. And the exponent, 2, becomes the logarithmic value over here. So the logarithm is equal to the exponent. And we call this logarithmic form. And everything that we discuss in this episode and in the next episode is going to be about logarithms and basically this notion of a logarithm as being this exponent written on the ground. Let me just ask you a couple questions here that also pertain to the last episode. Suppose I were to write the log base 6 of the square root of 6 equals x. Can anyone tell me what x should be there? Stephen?
1/2.
Is 1/2. Tell us how you knew that.
Well, because you can switch that and make it 6 to the x power is equal to the square root of 6.
Exactly. Okay, let me just write that up here first. So in other words, we have an expression given as a logarithmic in its logarithmic form. So what Stephen is suggesting is that we convert it to its exponential form, because you and I have been working with exponential forms for a long time. Logarithmic forms we just introduced in the last episode, so they're rather new to us. So 6 to the x power, you remember x becomes the exponent, equals the square root of x. So then what did you do, Stephen?
Well, if you take a number to the 1/2 power, it's the same as taking the square root of it, so.
Yeah, the square root of 6 means 6 to the 1/2 power, so it looks like x should be 1/2. So the number over here should be 1/2, exactly. Now let's take one more like that. What if we said the log of x is equal to 1,000. Now, I don't have a subscript given here. So what's the base that we assume when I don't put a subscript there?
10.
Base 10, yeah. So this is referred to as a common log, or a common logarithm. And if we convert this to exponential form, we'd take, yeah, that's a big number, isn't it? Yeah, well, let's go ahead and finish this. It's bigger than I expected it to be. So we have 10 to the 1,000 is equal to x. Oh my gosh, well that's a very big number, yes. But we can still work it.
Write it out first, then.
Yeah, you know what I actually meant to do was put the 1,000 inside, as you can probably imagine. But the answer is 10 to the 1,000 power, so that's okay. Okay, now let's go to the objectives for this course, for this episode. And we have 3 objectives. First of all, we want to establish 4 laws of logarithms that we'll discuss first. Then we will show that the inverses of exponential functions are logarithmic functions. So we'll establish that fact using the laws of logarithms. And then we'll finally conclude by discussing the graphs of logarithmic functions and transformations of those logarithmic graphs. Okay, well, the 4 laws of logarithms. Let's look at the 4 logs right here, the 4 laws. Right here, 4 laws of logarithms. Now, here's the first law. It says if you take the log base a of a number m, and if you add the log base a of a number n, you get the log base a of. Now, you would think that if you're adding the log of m and the log of n, that you might get the log of m plus n, but it's actually m times n. And the reason for this is, you see, what we're really doing is adding exponents. A logarithm is an exponent, as we've just mentioned. So if I add the exponent here and the exponent here, I get the exponent on the product. Let me just give you an example. Suppose we were to take the log base 2 of 4 and add on the log base 2 of 8. What is the log base 2 of 4?
2?
Is 2, yeah. Because remember, this is an exponent. It's the exponent you would put on base 2 to get 4 for an answer. So the question is, what exponent would you put on base 2 to get 4 for an answer? And the exponent would be 2. 2 squared is 4. So this number is 2. And what exponent would you put on base 2 to get 8?
3.
3. So this logarithm, or this exponent now, is 3. So we should get 5. Well, you see, if I use law number 1, the log base 2 of 4 plus the log base 2 of 8 is the log base 2 of the product, 32. And as a matter of fact, if you take the exponent 5 and take 2 to the 5th power, you will get 32. So I've added the exponent on 2 to get 4, plus the exponent on 2 to get 8, and I get the exponent on 2 that gives me 32. Or in this case, 3 plus 2 is 5. Let me just work another example of that. What if we said the log base 7 of 5 plus the log base 7 of 4? Now, right offhand, I don't know what the log base 7 of 5 is or what the log base 7 of 4 is, but can anyone tell me what is the sum of those two?
Log base 7 of 20.
It's the log base 7 of 20, and actually I don't know the value of that number either, but these two expressions are equivalent. This sum is equal to the log base 7 of 20. That's using the first law of logarithms. Okay, now for the second law of logarithms, for number 2, the log base a of m minus the log base a of n is equal to the log base a of, well, now let's see. When I added the two logarithms, I got the product. So if I subtract the two logarithms, I should get the log of the, what would you guess?
Quotient.
The quotient, yeah. Good guess. M over n. I'll put that in parentheses just to set it off. Let's take an example of this. Suppose we were to take the log of 1,000 minus the log of 10. Now, since I'm not showing a subscript, of course, these are base 10 common logarithms. And according to this rule, I should get the log of 1,000 over 10, which is the log of 100. Okay, so if I divide 1,000 over 10 by 10, then I can reduce that to be the log of 100. Now, tell me, what is the log of 1,000?
3.
It's 3, right. Let's see, Jenny, maybe you could just sort of explain how you got that.
I wrote 10 to the x is equal 1,000.
Okay, so she wrote 10 to the x equals 1,000, where the x is the logarithm value.
And I know that that's 3.
Yeah, you're right, 10 to the third. 10 to the third is 1,000. So she said, well, if this logarithm is the exponent is 3, so she knew the answer would be 3. And let's see, Susan, what's the log of 10?
I have no idea.
Okay, Jeff, what's the log of 10? 1. It's 1, okay. And let's see, I'll do this one on my own. 3 minus 1 is 2, okay, 2. But guess what? The log of 100 is 2. So here's an example of that sort of demonstrates the rule. But basically the purpose of the rule is to say what we're doing is subtracting two exponents. And when you subtract two exponents, you get the exponent that goes on the quotient. And this is a logarithm, so it's an exponent, and it's the exponent that goes on the quotient of the two. Okay, that is law number 2. Let's go to law number 3. Law number 3 says if you have a constant multiple of a logarithm, let me put parentheses around that to indicate this number is outside. So if I have a logarithm and I multiply it by some real number, that's the same thing as bringing the real number inside the logarithm, but you don't put it in front of the m, you put it as an exponent on m. So it's a totally different world here in logarithms. Things don't turn out the way you might first suspect. Let me demonstrate this. Suppose we were to take 2 times the log base 3 of 27. Well, actually, that's pretty big. Let's say the log base 3 of 1/3. The log base 3 of 1/3. Now, according to this rule, how would I rewrite that if I bring the 2 inside?
Log base 3 of 1/9.
Well, it'd be the log base 3 of 1/3 squared, which is 1/9, exactly. So if you bring the 2 inside, you don't multiply by 2, but you make it an exponent. Now let's see if this is really true. What is the log base 3 of 1/3? That is, what is the exponent you'd put on 3 to give 1/3 for the answer?
-1.
-1, right. So what this really says here is 2 times -1. Okay, now, do we get, let's see, that product is -2. Do we get -2 on this side? Well, if I reduce this, let's see, if I reduce this, 1/3 squared is, as Stephen just said, is 1/9. So what exponent would you put on 3 to give you not 9, but to give you 1/9? I think that would be -2. Yeah, 3 to the -2 is 1/9. So -2 equals -2. So this is not a proof, but it's a demonstration of that rule. Okay, now we come to the fourth law of logarithms. And you know, if you look in your textbook, you will see other properties of logarithms listed in the section on laws of logarithms. And technically, you could make this list longer, but I think the 4 laws that we're listing here are the ones that are most fundamental, and you can get by with just these 4. Suppose we have a raised to the log base a of m power. Now you notice I'm putting the logarithm up in the air like an exponent, because a logarithm is an exponent. A raised to the log base a of m, that has to be the same base as what I have down here. This answer is m. So if you take a number a and you raise it to a logarithm base a of m, you'll get m. I think maybe if I move that over a little bit, I can put an example right here beside it. Suppose we have 2 to the log base 2 of 8. What will we get? Well, can anyone tell me what is the log base 2 of 8?
3.
It's 3, yeah. Because this is the exponent that you put on base 2 to get 8 for the answer. So that's a 3. So that's 2 to the 3rd power. And 2 to the 3rd power is 8. Yeah, so that's exactly what the rule says. As long as the base here and the base in the logarithm are the same, then the answer will be whatever's inside the logarithm. In this case, it'll be 8. Okay, here's a different problem. What would be e raised to the natural log of 7? You may say, well, Dennis, we don't know what the natural log of 7 is. That's okay. I think you'll know what this answer is. Because when I say natural log, ln, what base am I referring to? Base e. And so if the base here, base in the exponential expression, is the same as the base in the logarithm, then the answer should be 7, right? Should be 7 using this rule. Now, this last rule, I think we can actually give a more formal proof for. Let me just erase this. And what I want to do is to prove the rule right here, because it's sort of probably the one that's the most striking, I think, of these 4. So let's see. Suppose I want to figure out what is a raised to the log base a of m power. So let's just look at this exponent for a moment. The log base a of m. Now, of course, we don't know what a is or what m is for the moment, but this has some value. Let's say we'll call it x for the moment. Now, how would I rewrite this in its exponential form?
A to the x equals m.
A to the x equals m. Yeah. These two things mean the same thing. Now, what if I replace x with what it's equal to? X is equal to the log base a of m. So a raised to the x, that's the log base a of m power. Okay, so all I've done is replace x with what it's equal to. I should still get the same answer, m, and there's our rule. That sounds like a little bit of sleight of hand, but if we kind of summarize it in a different way, it says what we're doing is we're putting a logarithm in the exponential position because a logarithm is an exponent. So if you put it where it naturally goes as an exponent on base a, then you will get the number m for the answer. Okay, we have these 4 laws spelled out on the next graphic. So let's go to that and just show them collectively here. These are the 4 laws. I think the only 4 laws that we need to know to work the rest of the problems in this episode and in the next episode. First of all, number 1 says if you add 2 logarithms together and they're the same base, the log base a of m plus the log base a of n, you get the log base a of the product mn. Number 2 is sort of the corollary to that says if you subtract 2 logarithms with the same base, log base a of m minus the log base a of n, you get the log base a of the quotient m over n. Number 3 says that if you multiply a logarithm by a constant, you can bring the constant inside by making it an exponent. C times the log base a of m is the log base a of m to the c power. And number 4, this last one that we just derived, says if you take a and raise it to the log base a of a number m, then that expression is equal to m. Okay, now let's go to the next graphic and we'll see in some examples where we can apply these rules. Okay, here we have an example where we want to rewrite several expressions in simpler logarithmic terms, and we're going to be using those laws of logarithms that we just saw. Now let's take, for example, the log base 5 of 25x cubed. Now, if we change that to a simpler logarithm expression, the first thing I notice is this is a product of two factors, 25 and x cubed. So if I use the very first law of logarithms, the log of a product is the sum of 2 separate logs. So this will be the sum of the log base 5 of 25 and the log base 5 of x cubed. Now, we can reduce each of these. For example, what is the log base 5 of 25?
2.
It's 2. Yeah, because you remember, what were you going to say, Jenny?
The wrong answer.
Oh, the wrong answer, okay. Well, this is an exponent, right? A logarithm's an exponent. It's the exponent you'd put on this base to get 25. So I think we want to square, so that'll be a 2. And what about this expression? We have the log base 5 of x cubed. Now, I don't think we can actually give a value to this because we don't know what x is, but there is another way I can write it that makes the logarithm look simpler using one of our 4 laws of logarithms. David, looks like you have an idea. What are you thinking?
I wasn't thinking.
Oh, he wasn't thinking. Okay. I just thought he was thinking. Well, let's see now. Look, we have an exponent inside, and if there's an exponent inside, I could bring it out as a coefficient. So I'll put that in front and say 3 log base 5 of x. Now you might say, well, Dennis, you're actually using this backwards, because when we stated the law, it stated that if you have a coefficient in front, it comes in as an exponent. But you see, it's really a two-way street. If you have an exponent inside, you can bring it out. And if you have a coefficient outside, you can bring it in as an exponent. So here is an expression that's equal to the log base 5 of 25x cubed. And this has a simpler logarithm expression in it. Now, when you compare these two, the one on the left and the one on the right, you may ask, well, which one technically is simpler? Because this one looks pretty simple. It's just a single logarithm. This one, in a sense, looks more complex. And I guess it's really debatable which one is simpler. This certainly has the simpler logarithm in it. But what's significant here is that we can change logarithms to other forms. We can change what's on the left to the right. And if I go backwards, I can change what's on the right back to what's on the left. OK, let's do this next one. This is a natural logarithm, so the base is what? Base e. So whenever you see ln, that means it's the natural exponential function, base e. E is about 2.718, more or less. OK, which law of logarithms would you use to begin to change this?
The second law we covered.
The second law, yeah. Because the log of a quotient is the, David, what would you write here?
Let's see, log. Hold on.
See, the log of
E?
a quotient. Pardon me?
I'm sorry. What were you saying? Go ahead.
We have the log, natural log of a quotient. And by the second law of logarithms, I can write this as a difference. What would the difference be?
You could put, would it be log e? Would you start off log e?
No, I'd put natural log of 6.
Natural
I'd
log
take
of 6.
Natural log of the numerator.
Minus natural log of e.
Minus the natural log of e squared. That was in the denominator.
Okay.
Now, if you were to write log base e, that's the same thing as ln, but ln's a little bit more compact. In other words, if you were to write log base e of 6 minus the log base e of e squared, that would be fine. It's just that standard notation is to use this ln rather than log base e. Okay, now, can I reduce either one of these? Ginny, which one or both can we reduce?
You can reduce that natural log of e squared to just 2.
Exactly, very good. Tell us how you arrived at that.
Because ln is base e, and if you're raising it, it's by that fourth law that
Right.
you wrote down that said
Right.
that if you have it to raised a power to the same power.
Yeah, now you remember this natural log is an exponent. It's the exponent you'd put on this base. I'll just pencil it in right below it. It's the exponent you'd put on this base to get e squared. Well, I think you'd want to put a 2 as the exponent on e to get e squared. So this expression is equal to 2. Now, the first one I can't reduce. That'll be the natural log of 6, but then minus 2. Here's another way of thinking of it. Let me just rewrite this expression right below it. Ln e squared. Now, someone may be thinking, now, if you have an exponent inside a logarithm, can't you bring that out in front? Well, yes, we can, and we would write it as 2 ln of e. And then at this point would say, what is ln of e? That's the exponent you put on base e to get e. That's a first power. So this is ln of 6 minus 2 times 1, and that's ln of 6 minus 2. Ginny found a faster way of getting there because she reduced this using the definition of a logarithm. Here, I used a property of a logarithm, but then eventually I had to go to the definition of a logarithm to get rid of the natural log there. But we get the same answer either way. Okay, now let's go to the last example. And let's see, let's go back to that graphic and look at example C. Yeah, we have the log of 10 square roots of 10. Now, you know, actually, I should probably put parentheses around this so that it's not misinterpreted. Because without parentheses, this could be misconstrued as being the log of 10 multiplied times the square root of 10. But what I really mean to do is take the logarithm of this product right here. Okay, well, with that understanding, let's continue. Can anyone think of a way of evaluating that using properties of logs?
First law.
The first law? Okay, so how would you write this, Stephen?
Log of 10 plus the log of root 10.
The log of 10 plus the log of the square root of 10. Okay, and what is the log of 10?
1.
Is 1. And what's the log of the square root of 10?
1/2.
1/2. And so our answer is 3/2. We get rid of all the logarithms that way. Can anyone think of another way of getting the same answer? Let's just go down below. What I'm thinking is, what if we actually combine these? What is 10 times the square root of 10? It's 10 to the what power?
3/2.
10 to the 3/2 power, yeah. You see, you're multiplying 10 to the first times 10 to the 1/2. And the rule says when you multiply like bases, you add the exponent. So 1 plus 1/2 is 3/2. And then the log of 10 to the 3/2 is 3/2. And there we have the same answer. Now, I'm not saying either procedure is the best way to do it. It's just these are two different ways of applying various laws of logarithms to arrive at this result. Okay, so on an exam, if you took one extra step or one less step than I did, that's fine as long as you're using the rules correctly and you arrive at the correct answer. Okay, let's go to the next graphic and we'll see a little bit different example, but still uses the same laws of logarithms. And let's see, I'd like to be able to write on that graphic if I can. Here we go. Okay, this example says, suppose that we have some base, I'll call it b, and the log base b of 2 is 0.35. And suppose the log base b of 9 is 1.12. And this is for some base b, but we don't know exactly what the base is. So the question is to compute each of the following. What would be the log base b of 18? The log base b of 18. Well, now, we know the log base b of 2, and we know the log base b of 9, and I'm thinking that this is the log base b of 9 plus the log base b of 2, because 9 times 2 is 18. I'm thinking of factoring 18 and then writing the log of each factor separately. And the log base b of 18, I think I can write that in just below here, is 1.12. And the log base b of 2 is 0.35. And if you add those together, you get 1.47. Now, here's the purpose of this activity. If you know a few logarithms, like in this case I know 2 logarithms, I can compute other logarithms based upon those. So by knowing just 1 or 2, you can begin to generate a whole list of logarithmic values. Here are some others that we can calculate. I'll put that answer over here, 1.47. By the way, you'll see all these worked out on the website. So if I say something too fast or if you miss writing something down, you can always look on the website and get the details there. The next question is, what's the log base b of 0.25? Well, now let's see. We don't have any fractions or decimals given. We're given the log base b of 2 and the log base b of 9. Do you see any connection with 0.25 and either 2 or 9? I'm thinking, here's what's going through my mind. I'm thinking this is the log base b of 1/4, because 0.25 is a fourth. And 1/4 is the log base b of 2 to the negative 2 power. And that's going to be negative 2 log base b of 2. Okay, here I'm using a property of logarithms. And this number we know. It's 0.35. So this is negative 2 times 0.35. And that tells me this is negative 0.70. That's the logarithm of log base b of 0.25. Okay, so given as a decimal, we don't recognize it as being related to 2 or 9. But when we convert it to a fraction, and then we convert it to an exponential notation, then I can use a law of logarithms to allow me to evaluate that.
Did you put something like that on the test?
Oh yeah. In fact, we can do another one in just a minute here if you'd like. Let's go ahead and do this last one, and then I'll make up 1 or 2 more. Okay. The log base b of the square root of 2/3. Let's see. Let's write that in right here. We have the log base b of 2. We have the log base b of 9. How are we going to do this? Well, first of all, how are we going to get rid of the square root?
Right. 1/2 power.
Put a 1/2 power. In fact, why don't we just go ahead and move the power out in front? I think people know what we're doing here. We're writing this as 2/3 to the 1/2 power. The 1/2 power comes out in front. So this is the log base b of 2/3. Okay, where can we go with that?
Oh, you can go to the log, you can divide it by the quotient rule.
Okay, so what will we write?
You'd have log base 2, log base b is 2, minus log base b of 1/3.
Well, let's see now. If you're going to say
Excuse me,
minus,
3.
yeah,
Log base
we'll
b of
have to
3.
put a 3 there. Okay. Now we know the log base b of 2, but do we know the log base b of 3?
It would be to the 1/2 power, log base b of 9 to the 1/2.
9 to the 1/2 power. Yeah. So let's write that in right here. 1/2 times. Now this log we know. This is 0.35 minus. And this is 9 to the 1/2 power. That's what 3 is. So if you put the 1/2 out in front, then you'll be taking the log of 9. And the log of 9 is 1.12. So I'm taking 1/2 of the log of 9 to get the log of 3. So this will be 1/2 times 0.35 minus 0.56. I think I'm just about out of room there, but that's going to be 1/2 of negative 0.21. Let me just go up here and finish that up. 1/2 of negative 0.21, and that's going to be negative 0.105. So that's the answer. Oh, yeah, that's the answer for this problem. Okay. Jenny, you were just saying, would we have problems like this on the test? Yes, we would. And you know, one of the purposes of this is we are computing logarithms of values that we couldn't find on a calculator. Let me just make up a new set of a new set of values. Suppose I have the log base b of, let's say we call this base c. And the log base c of 4 is, I'll just make up something, 0.14. And suppose the log base c of 5 is 0.118. So what would be the log base c of 10 if you're given those two? How could you get the log base c of 10?
5 plus 5 is 10. Can you do that?
5 plus 5 is 10. Also, 5 times 2 is 10. So if we think of this as being 5 times 2, see, if you have a product inside, you can break it up as a sum of logarithms. So I could write this as the log base c of 5 plus the log base c of 2. Now, how can I get the log base c of 2?
The square of the 4.
Well, take the square root of the 4. Yeah. So I could write this as the log base c of 5 plus 1/2 the log base c of 4, because that's actually 4 to the 1/2 power, and I brought the 1/2 power out in front. Now, we know all these numbers. This is 0.18, and this is 1/2 of 0.14. So we get 0.18 plus 0.07, and that's 0.25. That's the log of 10, log base c of 10. Okay, one more like this. Given those same values, how could I find the log of 25 times the square root of 20 base c? The log of 25 times the square root of 20. Well, this is all made up of 5s and 4s. So I'm thinking we could write this as the log base c of 25 plus 1/2 the log base c of 20. And this is 2 times the log of 5, log base c of 5. And this is 1/2 of the log base c of 4 plus the log base c of 5. Now, we have it broken down into all logs of 4s and 5s. So this will be 2 times 0.18 plus 1/2 of 0.14 plus 0.18. And that's 0.09 plus 1/2 of 0.32. What is half of 0.32?
0.16.
0.16. Now, what's 0.16 plus 0.09?
0.25.
0.25, 0.25. You know, that's the same answer we got in an earlier problem, but that was for a different base as well. Yes?
2 times 0.18, 0.09.
2 times, oops, back up here. Yeah, you're right. I made a mistake there. I took half of it, and I should have doubled it. Let's back up. That's okay. This should be, thank you, 0.36 plus, now over here we said that was 0.32. We took half of it as 0.16. Oh, you're absolutely right. Different answer. It's 0.52. Yeah, thank you. Okay, so that's the logarithm of 25 times the square root of 20 using these two given values. Okay, next idea. You know, on your calculator, you only have 2 logarithm buttons. You have a log base 10, or the common log button, and you have the log base E, or the natural log button. So you may wonder, Dennis, what if I wanted to calculate on my calculator like the log base 3 of a number, or the log base 7 of a number? That we don't have buttons on our calculator for that. Well, number one, there would be an infinite number of buttons required to do that, because there's log base 2, log base 3, log base 4, log base 5. I mean, there's no end to it. But it turns out you don't need any others, because you can calculate any logarithm base using the 2 bases on your calculator, using a formula that we call the change of base formula. Let me just show you how the formula goes, and then I'll show you where it comes from. If you have the log base, base b of m, that's equal to the log base a of m divided by the log base a of the old base b. Now, imagine that base a is a base that's available on your calculator, either base 10 or base e. then you could convert any other base to a common log or a natural log, and you could divide it out. Now, let me first of all show you where this comes from. We'll just write a little proof right below it here. Suppose I'm given the log base b of m that I'd like to evaluate, and I don't know how much that's equal to, so I'm going to call this x for the moment. Now, what is the equivalent expression for this in exponential form?
b to the x is equal to m?
B to the x is equal to m. But let's say base b is not one of the bases available on my calculator. So what I'm going to do is I'm going to take the logarithm on both sides of this equation, and I'm going to use a base that I know. Let's say base a is one of the bases that's available on my calculator. And I'm going to take log base a on the other side as well. So on the left, I took log base a of b to the x, and on the right, I took log base a of m. Now, if I bring the x out in front, this says x log base a of b equals log base a of m. And if I solve for x is equal to the log base a of m divided by the log base a of b. But x was equal to the log base b of m. So this is the log base b of m, because we were given x was that in the very beginning, and now we've calculated x to be this ratio. So the log base b of m is the ratio that we have up here called our change of base formula. Let's go to the graphic up here on the screen, the next graphic to come up, and we'll see this expressed. The change of base formula, as we've just arrived at, says the log base b of m is the ratio of the log base a of m over the log base a of the old base b. Now, we can use this to calculate some other logarithmic values. And the problem we have there is to find the log base 4 of 15. Now, if we come back to the green screen, I'm going to do this on my calculator. If you can zoom in on this calculator. Okay, so the problem that we had on the graphic was to find the log base 4 of 15, but you notice we don't have a log base 4 button anywhere on our calculator. So what I'm going to do is change this to a logarithm base that I'm familiar with. So let's take the log base 10, or just log of 15, but then I have to divide it by the log of the old base 4. So I'll just take this ratio and evaluate it in this form. So I'll take the log of 15 divided by the log of 4. And the answer, the answer is 1.9534. I don't know if you can see that very well on the screen or not, but it's about 1.95. Now, just below it, let me write this another way. We have the log base 4 of 15, and this time I'm going to change it to the natural log of 15 over the natural log of 4, because I do have a natural log button on my calculator. So I'm going to try taking the natural log of 15 and dividing it by the natural log of 4. And you see we get the very same answer. 1.953445298. So if I had yet some other base, like a log base 3 button, I could have taken this ratio using log base 3s, using the change of base formula. So you know what this tells me is, rather than having not enough buttons on my calculator, I really have too many. I don't really need both of those. I really only need one logarithm button, and I can find any other logarithm base. The reason these two are given is because common logs and natural logs, those two come up probably 95% of the time in applications, so they've been kind enough to give them both on our calculators. If we go back to that graphic on the change of base formula, let's look at the answers that were computed or is written on the screen. The log base 4 of 15, if you take log 15 over log 4, you get, this is rounded off, 1.95344. And if you take the log base 4 of 15 using the natural logarithm, you get approximately the same number again. So this is a formula that allows us to compute logarithms in any other base. Okay, now, yet another application of these laws of logarithms is the fact that if you have an inverse function, if you have an exponential function like 2 to the x, its inverse function will be a logarithm function, log base 2 of x. Now, it's been several episodes now since we talked about graphs of exponential functions, and we have yet to graph a logarithmic function. But the fact is that these two functions are inverses. And if you think back to some material we covered quite a bit earlier in this course, one way of finding out if two functions are inverses is to take their composition. And if I take the composition of these two functions on x, what I should get for an answer is x if they're inverse functions. That is, these two functions should undo what each other does, and I should get x. Now, if I take this composition, I think that's exactly what I get. Here's how. The composition of f and g means to take f of g of x. That's just what the composition means. And then to evaluate this, I'm going to substitute on the inside for g of x, and I'll put in the log base 2 of x. And then what does f do to anything? Well, whatever number I put in here, the answer will be 2 raised to that power. So what does f do to this? It'll be 2 raised to this power, the log base 2 of x. Now, by our properties of logarithms, what is 2 raised to the log base 2 of x equal to? X. It's equal to x. So it looks like these two functions are inverses because when I took their composition on x, I got x. Let's try it the other way around. Suppose I take the composition g of f of x. So that's g parentheses f of x. And to evaluate this, I'll substitute for f of x. F of x is 2 to the x. So this is g of 2 to the x. And what does g do to that? Well, g takes any number, and it takes the log base 2 of it. So g will take the log base 2 of 2 to the x. Now, using another property of logarithms, how can I reduce this? If we bring the x out in front, this is x log base 2 of 2. And what is the log base 2 of 2?
1.
Is 1. So this is x times 1, or x. So you see, in either order, my composition of functions on x gives me x. So these two functions are inverses of each other. Now, let's go to the next graphic. The inverse of a function f of x equals a to the x is the logarithmic function g of x equals the log base a of x. That is, the inverse of an exponential function is the logarithmic function with the same base. And vice versa, the inverse of a logarithmic function is the exponential function with the same base. Now, this allows us to graph logarithmic functions, and here are a couple examples. We want to graph, first of all, the function g of x equals log base 2 of x, and then g of x equals log base 6 of x. Okay, let's go to the green screen and look at those. First of all, I want to graph g of x equals the log base 2 of x. Now, we've never graphed a so-called logarithmic function before, but now that we know that this is the inverse of the function f of x equals 2 to the x, what I'm going to do is graph that function, and then if I flip it across the diagonal line y equals x, I should see the graph of the inverse function. So let's do that right here. I'm going to graph the exponential function, first of all, because we're quite familiar with these from earlier episodes. So we'll get our coordinate plane set up here. Here's the x-axis, here's the y-axis. Now, this function, this exponential function, has 3 target points. Can someone remind me what the target points are?
0, 1.
0, 1. Okay, we go up 1. Then what else?
1, 2.
Okay, if you go to the right 1, you go up the base 2. And if you go to the left 1, what happens?
Up 1/2.
You go up the reciprocal of the base 1/2. Okay, now we're not graphing the logarithm function, we're graphing the exponential function. And so this function has a graph that looks like this. Does it have an asymptote?
Yes.
What is its asymptote?
Y equals 0.
Right, y equals 0 or the x-axis. Now, if I draw in a 45-degree line, y equals x, right along here, if I flip this graph over to the other side, if I flip it over to the other side, I should see the inverse function appear, and the inverse function will be the log base 2 function. One of the things we pointed out several episodes ago is that exponential functions with bases other than a 1, not 1 to the x, but any other positive base, these are one-to-one functions because they pass the horizontal line test. And therefore, they have inverses. And it's only today that we're finding out what the inverses are. Now, when I flip this over, the point 1, 2 will become the point 2, 1 over on this side. Should be exactly the same distance either side, but my diagonal line's a little bit off. And the point 0, 1, when I flip it over, will become what? 1, 0, right here. And the point negative 1, a half, let me write that one down. Negative 1, 1 half, when I flip it over, it'll become 1 half negative 1. And even more than that, the horizontal asymptote, when I flip it over, will become a vertical asymptote. It'll be the y-axis. And my graph will look like this. But what I'm graphing here is f inverse of x. And f inverse of x is the logarithm function. So what I'm graphing is g of x equals the log base 2 of x. Now, you know, it really takes quite a bit of time if we're going to draw the exponential function every time and then draw the logarithm function. So here's what I'm going to do to speed this up. Rather than graphing the exponential function, I'm going to keep the target points in mind, and I'm going to do everything sideways. So you see here where we said we're going to go up to 0, 1, I'm going to go to the right, 1, 0. I'm going to go to the right. And instead of going over 1 and up 2, I'm going to go up 1 and over 2. And instead of going back 1 and up a half, I'm going to go down 1 and over a half, the reciprocal of the base. And I'm going to plot these 3 points. I'm going to keep in mind that I have a vertical asymptote at the y-axis, and I'm going to draw that graph, and I'm never going to see this one. Now, if on your homework you want to draw that graph in, that's okay, but just be aware that's not part of the logarithm graph. That's merely an aid to help you graph these. So let's do the other example that was on the screen there. The other problem was to find the log base 6 of x, or to graph it. So part B says to graph the function g of x equals the log base 6 of x. Okay, here we go. This time I'm going to graph it in a faster manner without drawing that exponential function. Okay, so to graph this logarithm function, I'm keeping in mind that its inverse, I'll write it over here, it's the inverse of 6 to the x. Now for 6 to the x, you'd normally go up 1, so I'm going to go to the right 1, because I flipped everything across that diagonal line. And normally I would go to the right 1 and up 6, so now I'm going to go up 1 and over 6. 1, 2, 3, 4, 5, 6, right here. This is 6. And how would I get to the third point? Go down 1.
And over 1/6.
And over 1/6. I'll have to kind of squeeze it in right there. And you see this function is coming in not horizontally, but it looks a little bit more horizontal than the last one does, and it approaches the y-axis very quickly. Now, as the base of the logarithm gets bigger, you tend to get flatter looking curves because they turn out so fast. And the reason is because the corresponding exponential function turns up so fast. Let me just graph one more like this, and then we'll look at transformations of these graphs. Suppose I wanted to graph this function. Capital F of x equals the log of x. So I want to graph the so-called common log function. Well, the base is base 10. So here's 1, 2, 3. Let's say 10 is out about there. Here's 1, 2, 3, 4, 5. 1, 2, negative 5. Okay, x-axis, y-axis. Okay, now to graph this quickly, what I'll do is just go over 1. And if I go up 1, I'll go over 10. So we'll say 10 is out there. And if I go down 1, I go over 1/10. Now that's even closer to the y-axis than 1/6 was a minute ago. And this graph comes in very flat. It makes a very sharp turn, and it comes down the y-axis. And this is the graph of the common log function f of x equals log x. You could graph this on your graphing calculator, and this is exactly what you would see. By the way, speaking of calculators, on the next exam, there will be a portion of the exam where you will need a calculator to compute logarithmic values and so forth. But for the graphing aspect, you'll need to know how to draw the graphs without a graphing calculator. Okay, can we go to the last graphic here and look at transformations of these functions? In this example, it says sketch these transformations of fundamental logarithmic functions. And these are going to be translations up and down, vertical transformations, horizontal transformations, stretches. We're going to be flipping them around. So let's take these one at a time. First of all, we have f of x equals 2 plus log base 4 of x. What is the 2 going to do to the graph?
Would it shift it?
I can't see it.
Oh, okay. Can we show the green screen?
There we go.
Yeah, what is this 2 going to show to the do to the graph here, David?
It would shift it vertically.
It's going to shift it vertically because you see this is actually the same thing as writing the log base 4 of x plus 2. Yeah, so this is a vertical shift. So I'm going to be graphing one of my fundamental functions, log base 4 of x, but I'm going to shift it up 2 units. So if I mark off my scale, okay, so when I shift it up 2, this is my new origin. Now, from this position, I'm going to graph the log base 4 of x. I should go over 1 unit to the right. If I go up 1, I should go over 4 units to the right. Let's see, 1, 2, 3, 4 is right about there. Let's take out those dots. This is 4. And if I go down 1, I should go over 1/4. So those are my 3 target points. And when I draw my graph, it still approaches the y-axis. It approaches it from a higher level. Okay, next function. Let's graph log of the quantity x plus 2. So back on the green screen, we have g of x equals the log of x plus 2. The log of x plus 2. Well, you notice this is different than before. We had added a 2 in front. Now we're adding a 2 directly on the x. What does that do to the graph, Jenny?
It's going to shift it to the left, too.
It's going to shift it to the left, too. Okay, so I'm going to be graphing the log base 10, but I'm going to be shifting it to the left, too. So here's how we do it. Let's see, those aren't quite even there. Okay, so if I shift it to the left, too, this is my new origin right here. And that says my vertical, that says that my vertical asymptote, which normally went to the origin, is now going to be going right through -2. So this is the line x equals -2. Now, from this position, I'm going to go over 1. And if I go up 1, I'm going to go over 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's actually 8 on the x-axis, but it's 10 from the new origin, or from the asymptote. And from the new origin, if I go down 1, I go over 1/10. You notice this time I had to bring my vertical asymptote over with me, so my graph looks like this. Okay, we have one more function on that graphic that we want to graph. This one is f of t equals 2 ln -t. Now this one's a little fancy here. Not just because we're calling the variable t, that's not really that significant. But we have a natural logarithm function. What is the 2 going to do to the graph?
A vertical stretch.
It's going to be a vertical stretch. And what does the negative do? When you put a negative directly on the variable, it's a flip. But David, what kind of flip is that?
It's a flip over the asymptote? Is that right?
It's going to be a flip around the y-axis.
Or around the y-axis.
Yeah. So we're going to flip it around the y-axis. So you see, we're going to have to plug in negative numbers for t so that -t will be positive so that I can take the natural log of it. So my graph is actually going to be going off to the left-hand side. Okay, let me take that arrow out because I think we're going to need a little bit more space here.
So is there a restriction on t that t has to be negative?
In this case, yeah, see on those other graphs, t was positive. And so when I flip it over, now the t's are going to be negative. So what I'm going to do is I'm going to go over 1 unit to the left. And normally if I go up 1, I go over e. Now I'm going to go up 2 and over e. 1, 2, 3. So e is about 2.7, so I'll put e right about there. Because I have to stretch my graph vertically, so I went up 2. And if I go down 2, I go over 1 over e, which is about 1/3. That's a negative 1/3. And therefore, my function is going to look like this. Now, let me just ask you, how can I look at this graph and determine what is the domain? What is the domain of this graph? You remember if we just press the graph onto the t-axis, I get the domain. So the domain here is all numbers from -infinity up to 0, not including 0. And what is the range? Well, if I press the graph onto the y-axis, I get the range, and it looks like it completely covers the y-axis. So the range would be all real numbers. Okay, well, I think we're just about out of time. Here's what we've done today. We looked at 4 fundamental laws of logarithms. Now, those 4 laws are what make logarithms significant. If we didn't have those 4 laws, the rest of this would, none of this would have happened. I've been using those 4 laws of logarithms through all of this discussion, and in the next episode, you'll see us use those same 4 laws of logarithms again as we look at applications of logarithms, but using logarithmic scales and some other applications. So I will see you for episode 19.